We deal with heat and temperature literally every single day. But how well do we really get the physics behind it all? It turns out the whole thing kicks off not in some fancy lab, but with a simple little puzzle you've probably run into a million times. Okay, picture this. You're in your kitchen, you reach into the utensil drawer, you grab a metal spoon, and it feels so cold, right? But then you grab a wooden spoon, and it feels, well, just room temperature, kind of neutral. But here's the thing. They've been sitting in the exact same drawer at the exact same temperature for hours. So what gives? To crack this little mystery, we've got to get super clear on what we mean by temperature and heat.
All right, so the key to that whole spoon thing starts with a really important distinction, and that's the difference between temperature and heat. Now I know, in everyday life, we kind of use them to mean the same thing, but in physics, oh no, they are worlds apart.
So let's break this down. Think of temperature as a property an object has. It's basically a measurement of how fast its atoms and molecules are vibrating or jiggling around on average. It's their average kinetic energy. That's why, say, a giant swimming pool and a tiny teacup can both be at 70 degrees. The average jiggle of their water molecules is the same. Now, heat is totally different. Heat isn't something an object has, it's energy on the move. It's the energy that's transferred from something hot to something cold. So here's the big takeaway. Temperature is about the energy inside an object. Heat is the energy that's flowing between objects.
Okay, so how do we actually measure all this molecular jiggling? Well, we've got three main scales you'll run into. There's Fahrenheit, which we use here in the US. Then there's Celsius, which is pretty much the standard for the rest of the world and for science. And finally, there's Kelvin. That's the big one for physics. As you can see, Celsius is super convenient. 0 for freezing, 100 for boiling water. But Kelvin is special. It starts at absolute 0, which is the coldest anything can possibly get. It's the point where, in theory, all that molecular motion just stops. And the good news is, we have simple formulas to hop between these scales. Now, the one you're really going to want to remember for physics is the relationship between Celsius and Kelvin. It's just simple addition. That makes a ton of calculations way, way easier.
Let's try a quick one. Say we've got a pleasant room temperature, about 25 degrees Celsius. To get that into Fahrenheit, we just pop it into the formula, and boom, you get 77 degrees Fahrenheit. And for Kelvin, it's even simpler. You literally just add 273. So 25 plus 273 gives us 298 Kelvin. See? Once you know the formula, it's really just plug and chug.
Okay, so we've got a handle on measuring temperature. But what about the energy it takes to change a temperature? This leads us to a super cool property of matter. I like to call it thermal inertia. It's like how stubborn is a substance when you try to change its temperature.
The official name for this thermal inertia is specific heat, and we use a lowercase c for it. It's literally a number that tells you how much energy you need to pump into something to raise its temperature. Water, for example, has a crazy high specific heat. That's why on a hot day, the beach sand can burn your feet, but the ocean is still freezing. The sand has a low specific heat, so it heats up fast. The water is stubborn, and the formula that puts this all together is this beauty right here. Q equals mc delta T. That C is the magic number, the measure of that thermal stubbornness.
All right, let's put this formula into action. Let's say we want to know how much heat, or Q, it takes to warm up 200 grams of water, that's about a small glass, by 10 degrees Celsius. First, we identify our variables. Make sure mass is in kilograms, so that's 0.2. The specific heat for water, C, is a constant you'll get to know well, 4,186, and our change in temperature, delta T, is 10. We just multiply them all together, and we get 8,372 joules. That's the amount of energy we need.
But hang on, what happens if you just keep adding heat to a pot of water? The thermometer goes up and up and up, and then all of a sudden, it just stops, even though you're still adding heat. This is where physics gets really, really cool. It's a concept I like to call hidden energy. So check this out. This is the heating curve for water, and it shows something that should feel kind of weird. Look, as we add heat to ice, its temperature goes up. Makes sense. But then it hits 0 degrees Celsius. And look, the temperature just flatlines. It stays stuck at 0 until every last bit of ice is melted. And then the same thing happens up at 100 degrees when it's boiling. The whole time we're pumping in more and more energy, but the thermometer just refuses to budge. So the big question is, where is all that energy going?
Well, that's our hidden energy. It's officially called latent heat, and we use a capital L for it.
This is the energy that's being used to do something else entirely, to change the state of the water, to melt it from a solid to a liquid, or boil it from a liquid to a gas, all without changing its temperature at all. And the formula for this? It's super simple. Q equals mass times L. And there are two main types of L you'll see. One for fusion, which is melting, and one for vaporization, which is boiling. Okay, let's run the numbers. How much energy does it take to melt 100 grams of ice that's already at 0 degrees Celsius? Well, we take our mass, 0.1 kilograms, and we multiply it by the latent heat of fusion for water. And look at the result, 33,400 joules. That is a ton of energy. And remember, all of that energy goes into just breaking the bonds holding the ice together. It doesn't raise the temperature even one tiny bit. And this really is the whole ballgame right here. During a phase change, the energy you add isn't making the molecules move faster. If it did, the temperature would go up. Instead, all that energy is being spent on something else. It's doing work. It's either breaking the bonds that hold a solid together, or it's giving liquid molecules the final kick they need to escape and become a gas. That is where all that latent heat is going.
Okay, so we've got our tool for when temperatures change. That's specific heat. And we've got our tool for when phases change. That's latent heat. So now let's bring it all together with something called calorimetry. You can think of it as the great equalizer.
The core idea here is one of the biggest rules in all of physics, the conservation of energy. Basically, if you have an isolated system, like a perfectly insulated thermos, no energy can get in or out. So if you mix something hot and something cold inside it, whatever heat the hot thing loses, the cold thing has to gain. It's a perfect trade. Nothing just disappears. Which is why we can say that the heat lost plus the heat gained adds up to 0. They cancel each other out. Let's put this to the test. Imagine we mix 100 grams of pretty hot water at 80 degrees with 200 grams of cooler water at 20 degrees. What's the final temperature going to be? Well, we start with our main principle. Heat lost equals heat gained. We use our Q equals mc delta T formula for both sides. Now, here's a neat trick. Since both things are water, the specific heat, C, is the same on both sides, so we can just cancel it out. Makes the math way cleaner. From there, it's just algebra. We plug in the masses and temperatures we know, and we solve for the one unknown, our final temperature, TF. A little bit of shuffling the terms around, and we land on a final temperature of 40 degrees Celsius.
All right, so we know how to calculate how much heat moves around, but we haven't really talked about how it gets from point A to point B. There are 3 main ways heat travels, and this is what's going to finally solve that spoon mystery we started with. Okay, first up is conduction. This is heat transfer through direct touch. And this is the answer to our spoon question. Metal is a fantastic conductor. When you touch it, it immediately starts sucking heat away from your hand really, really fast. Your brain interprets that rapid heat loss as cold. Wood, on the other hand, is a terrible conductor. It's an insulator, so it doesn't pull heat away from you quickly, and it just feels neutral. The other 2 ways are convection. That's heat moving through fluids, like the currents in a pot of boiling water. And finally, there's radiation, which is heat traveling as electromagnetic waves, like the heat you feel from the sun. The wild thing about radiation is that it doesn't need any stuff to travel through. It can go right through the vacuum of space.
Whew, okay, that was a lot. So let's pull all of this together and build a simple toolkit. The essential things you need to know to tackle these kinds of problems. So here they are, your 3 go-to equations. First up, Q equals mc delta T. Your first question should always be, is the temperature changing? If the answer is yes, this is your formula. Now, if the temperature is not changing, but the substance is melting or boiling, you use your second tool, Q equals ml. That's for phase changes. And finally, if you're mixing 2 things together and need to find where they end up, you use the big principle, heat lost plus heat gained equals 0. That's your foundation for all calorimetry.
So I'm going to leave you with one last question to think about. We said at the very beginning that heat flows because of a difference in temperature. But what if 2 things are at the exact same temperature? Can heat still flow between them? Think about a glass of ice water. The ice is at 0 degrees, and the water right next to it is at 0 degrees. Is any energy moving around in there? Thinking about that will take you even deeper into this stuff. Thanks for watching.